times the norm of x minus x naught.
Yes. So as x approaches x naught, t of x minus t of x naught approaches 0.
So we can let epsilon, yeah, very good. Yeah, so this goes to 0 as
That t of x approaches t of x naught.
if you're willing to say this kind of thing. But on the other hand,
We should, so we're going to use it.
okay, cool. Of course, it's also obvious. It's also obvious that if you made epsilon greater than 0, you pick delta equal to epsilon over the norm of t, and then for x minus x naught less than delta, that implies that the norm of t of x minus t of x naught is less than epsilon.
Yes.
And then you need a separate argument when t is equal to 0, but
I was told epsilonics were amateurish.
you were told epsilonics are amateurish?
Yes.
Who would say such a thing?
Zero notation.
Dang it. I think we just straddled the video. Like that argument just went right over the hour mark. That is so annoying. Let's go on here.
Maybe almost lunchtime.
Well, almost lunchtime is not lunchtime, so let's go on. So it turns out that every linear operator on a finite dimensional normed space is continuous, exercise 5. On the other hand, every infinite dimensional normed space has a discontinuous linear functional. The construction of discontinuous functionals depends on Zorn's lemma. Ooh, exciting. So I think I gave you one of those exercises, so I guess you'll get to use Zorn's lemma. We have now reached the discussion of the Banach spaces. Very good. What is a Banach space?
Is it norm vector space? The property.
Definition. If V is a normed linear space which is complete, obviously with respect to what? The metric. Yeah, the metric induced from the norm. Then V is a Banach space. All right. So examples of Banach spaces include Rn, Cn, LP, even the space of bounded real-valued functions on a set S with the sup norm. These are all examples of Banach spaces. And so the space of bounded continuous real-valued functions on a metric space is also a Banach space. However, the space of continuous functions on 0 to 1 is not complete and hence not a Banach space. So, examples. Rn, Cn, LP, what do we just say here? You know, but what's not an example is not Banach. The C0 one, where we define the norm of f was the pth root of the integral from 0 to 1, the absolute value of f of x to the p power dx. Turns out that space is not complete and hence not a Banach space. All right. Now, there are three major theorems left in this section. Let's write them. I don't think it's at all obvious, by the way, why the continuous functions from 0 to 1 are different than the other examples. So like that exercise is worth doing. So here's theorem 7.6. Let Tn, n equals 1 to infinity, be sequence of continuous linear operators from normed linear space V to a Banach space W. Suppose that the supremum over n of the norm of Tn is less than infinity, and the limit as n goes to infinity of Tn of x exists for x belonging to a dense subset. What does that mean of V? That meant that the closure of that subspace, of that subset, is all V, right? Then there exists a continuous linear operator, T, which goes, of course, from V to the Banach space W, such that T of x is equal to the limit as n goes to infinity of Tn of x. For each x, not in just the dense subspace, not just in the dense subset, but actually for all of V. Moreover, the norm of T is less than or equal to the limit as n goes to infinity of the infimum of the norm of Tn. All right. Then theorem 7.7 and theorem 7.8 round out this discussion, which we'll come back to next time, perhaps after lunch. Yes, we require food. Hey, we just had a snack. Anyway, that's a good place for us to stop and start again.